So here is quick summary of exponential modulation, also known as angle modulation. So now here are the parameters which we will be discussing, because these parameters will be frequently calculated for various calculations, and here is FM and PM. So we will see how these parameters are calculated for FM and PM. And it's not that we have to remember all these formulas, because if you understand the concept, these things can be derived very easily on the instant, on spot, right? So we will also then have a general example here, where we will see that the exponential modulated waveform is given to us, and we do not know which type of wave it is, and we will calculate all these parameters for this exponential modulated signal, where it is not known whether it is FM, PM, or anything in between them, right? So let us begin by first of all seeing the equation. So for the equation of general angle modulation or exponential modulation, EM for short, is A cos omega ct plus psi t. Now this psi t is the portion which is modulated by message in various ways. For your frequency modulation, here you have integration of message signal multiplied by a constant, and for phase modulation you take this mt as it is. So this psi t is in general a function of your message signal, and that is how your combined angle of this carrier is modulated. So these are various ways in which we can modulate that, and these are not the exhaustive possible ways. As we have discussed earlier, there can be many other possibilities between FM and PM. Now then we introduced the concept of instantaneous frequency, right? Instantaneous frequency is defined as the first time derivative of complete angle theta, and this theta angle is whatever is written inside this cos. So for this particular thing, it would be simply omega c plus psi dash t for this particular equation. For this thing, if you see, it is omega c because of this term, and since this is an integral signal, so the differential of this will be simply mt, so kf into mt. Similarly for pm, the instantaneous frequency will be omega c plus kp m bar t, because you have this signal here. So you see that instantaneous frequency is not omega ct. This omega ct is not called as instantaneous frequency. This is a mistake that people do frequently. Instantaneous frequency is the first time derivative of your complete angle that you have, right? So we do not bother whatever is written inside this, we take the first derivative of that. Then we talk about the power of exponential modulation in general. So we know that power is usually calculated by looking at the amplitude, and here the amplitude is A, and irrespective of whatever is written inside this bracket, this A remains the same, because this is not the case for amplitude modulation. So power will be A square by 2 always for this tone signal, right? Then frequency deviation. Frequency deviation is a term which we have defined in the previous video, and this frequency deviation is nothing but it is the deviation of instantaneous frequency. The deviation of instantaneous frequency, you see the instantaneous frequency here, and it has got this constant component omega c, and then you have this kfmt. Similarly here, if you will see, you have got instantaneous frequency, some component is constant and some component is variable. So what is the maximum value of the instantaneous frequency, or the minimum value of the instantaneous frequency? So we take that as the frequency deviation. So this delta f is nothing but delta f is equal to, for this particular case, kf into mp by 2 pi. If you take it in terms of delta omega, this 2 pi factor will not be there. And how do we arrive at this? If you take the value of kf as is, because omega c is constant, so from this frequency how much we are deviating at max, so that is kf into maximum value of this particular signal mt. So let us say that this signal mt lies between minus mp and mp. So in that case, kf into mp over 2 pi will be the frequency deviation here. However, for phase modulation case, if you see, it would be kp into the maximum value of this particular signal. So kp into maximum value of this particular signal is this, means the derivative has maximum value. This derivative's maximum value is equal to mp, this bigger dash. So we represent it by this notation, and that's why this frequency deviation comes into picture. And this frequency deviation, remember, it's calculated from instantaneous frequency, right? Not from this omega c. right? And then we come to, for if we have the signal bandwidth as b, then what do we mean by deviation ratio? There are two types of bandwidths, first of all. One is the bandwidth of modulating signal or the message signal, and second is the bandwidth of the final angle modulated signal. So by this B, we mean the bandwidth of the message signal or the modulating signal. So if that has a bandwidth of B, then frequency deviation ratio is defined as beta is equal to delta F over B. And we already know delta F from these formulas, so simply we have to define it. Delta F is here, and B is if you want to calculate bandwidth for this particular signal, you have this message signal here is empty, then maximum frequency of empty will be its bandwidth, because it's essentially a baseband signal. So whatever is the maximum frequency component available there will be the frequency of that. Similarly, for phase modulation case, it will be the maximum frequency of derivative of empty, right? So because here the signal that you have is empty, and you have to calculate the bandwidth by considering again this thing. So m dash t is there, so the maximum frequency in m dash t has to be there. And usually this parameter of bandwidth is given in questions, and we have to use that particular value. Then you talk about phase deviation delta phi. This phase deviation is the maximum value of angle of psi t. Now psi t is this. The what is the maximum value of this angle? So phase deviation is calculated from the total angle in the original signal. It's not calculated from instantaneous frequencies. It's calculated from this complete angle here, the portion that is apart from this omega ct plus psi t. So what is the maximum value of angle of this? So delta x for frequency modulation, if you see, it is maximum angle of this particular thing, because here the value of psi t is this, and similarly here the value of psi t is kp into mt. So kp is a constant term, so it can be removed because it won't contribute to any angle. So it's just the maximum value of angle of mt. Similarly here also you can remove or keep kf, there is no problem there, right? So this is how you calculate phase deviation. And then bandwidth of exponential modulated signal, it is represented by b of em. This b of em has to be there, and this is twice of delta f plus b. B, we know that it's the bandwidth of your modulating signal. It is calculated again from this instantaneous frequency. As you saw here, it was due to mt, and here it was due to m bar t, right? Although m bar t is not the modulating signal, but you have to bring it in this particular format, omega it first, and whatever remains after omega ct, you have to take the bandwidth of that particular signal. So this is Carson's formula. We have already discussed this Carson's formula in previous video.